Alright, so in this, nitrite, NO2 negative. In this case, you should have got nitrogen as the center. And yes, I'm going a whole lot faster on this because you should be picking this up on Monday. You will have a practice sheet on this so you can get crack-a-lacking with it. We can finish up this section with bonds and get into Vesper. We may actually be getting into nomenclature even sooner. This is going great. Get everything full octet. There goes everything full octet. There's step 2. Step 3. 3 is all about finding out the number of valence electrons we already showed. So I have 1 nitrogen and 2 oxygens. I have 5 valence electrons per nitrogen. 1 times 5 is 5. Then I have 6 valence electrons per oxygen. 2 times 6 is 12. Add those together gives me 17 electrons. But then I have to take in the negative charge into account here. Since I have a negative charge, it means I've added electrons. So I add 1 electron. And I must show 18 electrons. Count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm showing too many. So we fix it.
Take 1 off oxygen.
Take 1 off oxygen and nitrogen and then add it to the middle.
Put a double bond.
Or double bond, yeah.
Equal sign.
Double bond.
Equal sign.
Well, let's do this. I don't like those. I like those up there.
That's 18. I actually got that right.
So we're going to count it up now. Make sure we're good.
Oh.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm showing 18. Yes.
Will your number always be positive or will it not positive? Even?
Yes. Alright, so in this, only other thing we got to do is look for the charge. In this case, we're going to mentally, not visually, mentally split the bond. Electron pops here. Oxygen normally has 6 electrons. So 1, 2, 3, 4, 5, 6, 7. -1, so that oxygen has a negative charge on it. And then this nitrogen normally had 5. Split the bonds. 1, 2, 3, 4, 5. Showing 5. 0, it's neutral. And then this oxygen normally has 6. Split the bonds. 1, 2, 3, 4, 5, 6. So it also is neutral, which is good because we have a negative overall charge, which means all the charges from the atoms should add up to equal to that. Now, the only thing we're missing here.
So you need that negative in front of all of it, or just the oxygen?
Just that oxygen.
Okay, so that's the only time.
There was a second spot we could have put the double bonds. So we must show resonance.
Can we just leave it with that?
No, and I'm so happy you asked. Because today we're going to discuss as to why you cannot leave it like that. You must show the resonance that looks like just a mirror image of it, but it's not.
Ah.
You pretty much flip it.
Pretty much what you see. But this is why I'm not huge on Lewis structures. These are all two-dimensional things. But this is not two-dimensional. This is a three-dimensional molecule. So in this, make sure I got my video. My video has disappeared. I have now found my video. It's now playing an ad. It's now playing another ad. Yes.
When you do like your 6 money statement, thing, is that the numbers that were taken off of the
The first number, sorry.
The
6. Yep.
Then how do you get the 7?
I get the 7 because I split. So you split here, and it's like an electron goes here, and then an electron goes there.
Okay.
But if you split it, like visually, you have to redraw it.
Okay, I'm just making sure on this, and I'm pretty sure I have it, but I just want to make sure 100%. We have a test. So how to find it is you look up the number and you minus 1, or you minus 1 from the top. Minus 1. How do you do it?
It's a column. It's
So like oxygen, it's 6.
16th column, 6 valence electrons.
Okay, so what if it was like 4? Is it 13? 7 or 7?
7 valence electrons, 17th column. Alright, so in this, have you guys ever heard of a drug called thalidomide?
I think I've seen it on Facebook.
Thalidomide was a godsend, so people thought. So it was the medicine of all medicine, that it was going to solve a problem, take suffering, pain away, and it was like, yes. I mean, this medicine was literally, it was going to be better and a whole lot more famous than Viagra is today.
Oh my God.
Viagra was discovered by accident. Did you not know that?
It was heart medicine.
It was developed as heart medicine for patients that had heart attacks. They thought they had found the muscle receptors to help with the heart, and they had no idea. They got all the way to where they were doing tests on humans. They was in human trials, and more people died from heart attacks that was taking Viagra than weren't, that had the placebo. So they started meeting with people and figuring out the side effects from it, and whenever they started talking about side effects they had, it was like, boom, baby, we just hit the jackpot. And this medicine, thalidomide, was going to be even better because thalidomide was a special drug that cured women's morning sickness. You literally would take 2 pills, no morning sickness, no vomiting, done. And thalidomide is the perfect example to talk about whenever you're looking at resonance and how resonance matters.
In the fall of 1960, Frances Oldham Kelsey was one of the Food and Drug Administration's newest recruits. Before the year was out, she would begin a fight that would save thousands of lives, though no one knew it at the time. Although she was new to the FDA, Kelsey was no novice as a scientist. After graduating from high school at age 15, she enrolled at McGill University in Montreal and earned both undergraduate and master's degrees in pharmacology. From there, she applied for a research post at the University of Chicago's Pharmacology Department. Her acceptance letter was addressed to Mr. Oldham. Kelsey later joked that had her name been Elizabeth or Mary Jane, her career might have ended there. Fortunately, it didn't. She earned her doctorate in pharmacology and accepted Chicago's invitation to stay as faculty, where she undertook pioneering research on drugs and field safety. In 1950, she earned an MD, her 4th and final degree. By the time she joined the FDA, Frances Kelsey was one of the most educated, experienced scientists around. Yet, as the newest member of the team, Kelsey was assigned what everyone thought would be an easy review, an application from the U.S. drug company Merrill to sell a drug called thalidomide. Thalidomide was a sedative developed in Germany that was already being widely used in dozens of countries to treat insomnia and workplace stress. Thalidomide's anti-nausea properties also made it a popular remedy for pregnant women with morning sickness. Reviewing Merrill's application, Kelsey found its data on thalidomide's absorption and toxicity inadequate. Today, the FDA classifies drugs based on their safety for a fetus. But in 1960, many experts believed that the placental barrier shielded a fetus from harm. Kelsey's earlier animal-based research demonstrated the opposite. Drugs could pass from mother to fetus through the placenta. Like other drug companies at this time, Merrill had not tested its drug on pregnant animals. Kelsey later said Merrill's evidence for thalidomide's safety seemed more like testimonials than the results of well-designed studies. Kelsey rejected Merrill's application and asked them to submit a second, backed by better evidence. Her FDA colleagues supported this decision. Merrill had expected a quick affirmative reply so it could launch thalidomide for the holiday season, when sedative sales soared. Instead of supplying Kelsey with the data she requested, they first tried to convince her to approve the drug over a series of calls and visits. When these failed to sway her, Merrill executives complained that stubborn and nitpicking Kelsey was the problem, not thalidomide. The FDA backed Kelsey, forcing Merrill to file another application, and another, and another. As Kelsey reviewed and rejected each new application, news of thalidomide's adverse side effects began to surface. Doctors reported cases of nerve damage in early 1961, and by fall, they'd unmasked a more horrible truth. Thalidomide, widely used by pregnant women, caused severe birth defects. Thousands of babies died in utero, and tens of thousands more were born with extra appendages, shorter limbs, or no limbs at all. In November 1961, thalidomide was pulled from the German market. Nonetheless, Merrill continued trying to get it approved in the U.S. for several months before withdrawing their sixth and final application. While Kelsey wasn't the only scientist to identify the risks of thalidomide, she sounded the alarm that kept it off the multi-billion-dollar American drug market. As public awareness of the thalidomide tragedy grew, the quiet scientist became a media sensation. Headlines in newspapers and magazines heralded her heroism, while a smiling President John F. Kennedy presented her an award on the White House lawn. After the thalidomide scare, Congress passed laws that expanded
For whatever reason, it restarted.
In the fall of 1960,
She said, "Psych."
requirements for new drug applications. Kelsey was tapped to head the agency's drug investigation branch. Working at the FDA in different capacities into her 90s, Kelsey was able to witness the changes her actions helped inspire. Her visibility may have dimmed since, but her legacy endures. Privileging facts over opinions, and patience over shortcuts, she made evidence-based medicine the foundation of reforms that continue to protect people today. We are inspired by Frances Kelsey's story, and we hope you are too. But Dr. Kelsey's life-saving work was almost thwarted by the pervasive gender biases of the 1930s. When offered her job at the University of Chicago, she felt pressured to refuse it because, according to Dr. Kelsey, when a woman took a job in those days, she was made to feel as if she was depriving a man of the ability to support his wife and child. Today, women make up almost 40% of the work.
This is why we should go with Apple. All right, so this was the whole thing with thalidomide that led to problems. Now, I'm going to mention some stuff that you're not going to learn about until you take an organic chemistry class. So some things you're just going to have to accept for right now. So, first thing you got. Put it away. Put it away. You have these things we call enantiomers, and within these are talking all about resonance. Okay, and for example, we label stuff with R and S. So let's say that this is the R enantiomer, and let's say this one is the S enantiomer. And all that's talking about is the shapes of these molecules. Because in this, it's three-dimensional. So within it, it would say certain things will be coming out towards you and certain things will be going back. And it's so important. The shape of the molecule is just as important as the molecule itself. And this is as to why. From research, they found out what the problem was. The R enantiomer was golden. It was perfect. It's what was curing morning sickness. so women could take the R enantiomer, but they couldn't take the S enantiomer. The S was what was going through the placenta to the fetus and causing all the birth defects. So in this, the grand scheme idea was just get rid of the S enantiomers and we'll be fine. Just give pregnant women the R enantiomers. Well, it's wrong, because for no reason whatsoever, the R enantiomer randomly inside the body decides to just flip and turn to the S enantiomer. And whenever it does that, it changes the structure and keeps causing birth defects. Therefore,
those two are like completely different. The two structures are completely different.
shapes and how they'll act in the body. Same molecule, different shape. So in it, doesn't matter, and that's why to this day thalidomide is not allowed on the market, even though it cured women's morning sickness. It's killing babies. This is why resonance is important. This is why you must show resonance, and why resonance must reign true. Now, time to put you to the test. Give me proper Lewis structure. Ammonium. Polytopic. The what? NH4 plus. Ammonium. This one should not take long, because I have one last baby to throw out there at you. Prepare you for your weekend.
Is it the smallest electronegativity or the largest?
Smalls. I'll give you one more minute and that's it. Alright. In this, you should have the center atom, nitrogen. Draw a skeleton, so bond the other 4 atoms, which is hydrogen, to it. Give everything a full octet where required, so we don't touch it. Because hydrogen is a rule breaker. It only forms one bond. If you went around and you start putting dots around hydrogens, you are wrong. Please do not do that. Every year I have kids that do that. It drives me nuts. Nitrogen has 4 bonds, so 8 electrons. It is good. Calculate how many valence electrons we have to show. We have 1 nitrogen and 4 hydrogens. 5 valence electrons per nitrogen and 1 valence electron per hydrogen. In that case, 5 plus 4 is 9. I have to show 9 electrons. Wait! We have a positive charge, which means we have lost an electron, so we subtract 1 electron, and I must show 8 electrons. Am I showing 8? Yes, in the 4 bonds. And this is the last part. The one area where people will just stop here and I tricked you. How many valence electrons does nitrogen normally have? 5. How many, when looking at charge-wise, does it have right now? 5 minus 4 is plus 1. That nitrogen has a positive charge. Remember, charge in the molecule must match the charge of the overall. And last, but not least, my favorite Lewis structure to do. Phosphate. PO4, 3 minus. I will give you till 12:20 to try this on your own. I'm going to need at least 3 minutes to get through this quickly to show you an important concept. Alright, so I think everybody's pretty good to here. You can get the skeleton, give a full octet, calculate out the number of electrons you have to show. Only thing is watch here. I got 29 because of the phosphorus and oxygen, but this 3 negative, I've picked up 3 more electrons, so I have to add 3 to that to give me 32. And be careful. Count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. We're showing the right number. Only other thing we have left to do is to show charges. So in this, hopefully you can see that all these oxygens are the same. These oxygens normally start with 6 valence electrons, minus, they're now showing 7, because we split the bond in half, the electron comes over here, gives me -1. So it looks as if we're in trouble, because we have 3 negatives, and I'm showing 4 negatives. But look at the phosphorus. Phosphorus normally has 5. In this case, it's showing 4. which equals a +1. So phosphorus is positive. But this is why I love phosphate. Phosphorus is a rule breaker. Phosphorus will break the octet rule if and only if bonded with oxygen, fluorine, or chlorine. In this case, it's bonded with oxygen. And I can throw in a double bond and get rid of these charges. So, for example, if I throw this double bond right here, phosphorus breaks the octet, so all these bonds are fine. But oxygen can't break the octet, so I have to take a lone pair off. You can count it up. I'm still showing the 32 electrons. But now I've changed it. This oxygen's changed. It normally has 6 valence electrons, and now it's showing 6. It makes it neutral. So now that negative charge is gone. And the same thing for the phosphorus. The phosphorus normally has 5 valence electrons, and in this case, you split the bonds in half, and you find out it's got 5 as well. So now it's neutral. So I still have the 3 negatives, and the only other thing I got to do is add the resonance structure.
So you couldn't just leave it like that?
Cannot leave it. And then you have to draw the other 3 resonance structures.
What?
There's 3 different spots that no longer go in.
Why do I feel like a test just throwing a really big version of skeleton?
I got everything up to where you took off the extra parts and added.
Yeah, I did too.
Yeah, because I was shocked about it.
The only thing like I was in trouble with is the numbers. I don't know how to explain it.
Bamboo, my beam, there's phosphate. All 4 of them.
What would you do with skeleton that had